Okay, good afternoon, everyone. Today, welcome to the sixth day or final day of our ATAL Online Faculty Development Program 2025-26 on Next Wave Advancement in Next Generation Communication. Today, we have three sessions, and after the three sessions, there is an examination and feedback. Then sorry for the interruption. There is a network issue is there. Net was disconnected. So, am I audible to you all?
Yeah, yes.
So, let me introduce Mr. Ankit Bhattacharya, Dr. Ankit Bhattacharya. He is currently serving as a technical lead of in the antenna R&D team in ACL Technologies, Chennai. He earned his PhD from IIT ISM Dhanbad in 2023 with a research focus on planar reconfigurable antenna. Following the completion of his doctoral studies, Dr. Bhattacharya began his professional career as a lead engineer of at ACL Technologies, Chennai. He subsequently joined Newcurrent, a US-based company operating in Bangalore, where he was involved in coil design and optimization for wireless power transfer applications. Thereafter, he transitioned to academia as an assistant professor at Amrita Vishwavidyapeetham, Andhra Pradesh. Dr. Bhattacharya has authored several research articles in ACI Index journals, including IEEE Antennas and Wireless Propagation Letters, AWPL, and has presented his work in various international conferences. He has also served as an active reviewer of several reputed journals over the past few years. His current research interests include the design and development of base station antennas for next generation wireless communication systems. So over to you, Dr. Bhattacharya, and our station, our session 11 starts now. Please, over to you, Dr. Bhattacharya.
Yes. Yeah. Thank you so much. Am I audible now clearly?
Yes, yes, you are audible.
Yeah, thank you for the nice introduction, and I'm really thankful to the organizing team to invite me, and I'm really feeling happy and honored to be part of this program. So I will just, yeah, definitely I'll going to uh, present my research area, but I'll try to give an overview, as lots of faculties from different part of our country is joined here. So I think many of you like are working in this RF domain or antenna domain. So I try to give you some overview where you can like continue your research in this domain, and what is the future trends uh, currently we are, what kind of work we are doing. I'll try to focus more on that. Basically, obviously I'll start with some basics of antennas and definitely wireless communication part, but I'll more focus on what is the major difference between industrial and academic research, because that is, I think, really necessary to understand. Okay, so let me share my screen. Okay. So is my screen visible?
Yes, yes, it is visible.
Okay, thank you so much. So okay, so like I have selected this topic like advancement and current trends in antenna technology, especially for the base station application, because currently I'm working in ACL Technologies, where we have a small R&D team who are mainly working for the Ericsson, who is actually the Ericsson antenna system is from Germany. Mainly their R&D team is working in Germany. So mainly we work for them, and we like extended team of Ericssons, but though we are working in ACL, but we generally work for only Ericsson right now. But we have separate R&D team also who are working in some other RF circuits and domain. But specifically, we are working in this base station antennas. Okay, so yeah, definitely, as I mentioned, like I'll go through some basics first, basics of base station antenna, some arrays and all, and then I'll slowly move to the majorly into the base station antenna development, design development, and measurement part. So let me first tell you that our team is mainly working uh, in both simulation and measurement. Okay, so we have all the facility, measurement facility at Chennai, and also simulation wise, definitely we have a good team who are like involved in developing the latest or R&D projects for the Ericssons. Okay, so I will start with this cellular communication, that evolution of cellular communication. And I think the we are the maybe the 90s kids or generation is the last generation, I think, who have seen all this transition from starting from 1G, 2G, 3G. So we are really lucky that we have seen this development. Okay, so if I start with the 1G communication, right, in 1980s, when only analog voice is possible, right, only voice communication. So this is a very good representation, this picture, which shows you that how fast it has grown, right, from 1980s and 2020. In this 40 years, we have seen that there is a like huge change in the especially in the wireless communication. And if you talk about the mobile phones, we know that how much it has changed, right? Currently we are using 5G already, and we are hoping that in next few years we will get the 6G also, right? So with the introduction from 1G cellular network in 1980s, and it has a substantial progress, and with the new generation uh, net, mainly what we actually have observed, our the first thing which comes into mind is the speed, right? So internet speed, that's more technically we can say network speed, the capacity, right? Functionality have improved and enable more advanced mobile device and apps. Next generation mobile networks like 5G or 6G provide much faster connection, communication, right, and with higher data rate. So that is the most common terms that we have seen when we are talking about the different generation, that is the data rate. So I think like Geo has, when Geo has introduced that 4G around 2012 or 13, we know like that speed from 3G to 4G, that was huge, or that transition was huge, right? So spectral, if now if you talk about more like technical word, then channel capacity, spectral efficiency, that is okay. But as a like from the user point of view, we want more speed, more functionality, right? So whenever now we are talking about functionality, means at the same time you want to access everything, like every wireless communication system like Bluetooth. Now Bluetooth is now almost outdated thing anyway, but that near field communication, then GPS, we always turn on GPS, and at the same time we are also getting phones, at the same time we are also internet surfing is going on. So at the same time we want to access at least 3 4 different wireless technologies, right? So definitely our mobile, not all our wireless device should have that capability and should have that much of bandwidth and data rate, so that everything is possible at the same time. So data rate is, that's why important when you are talking about multifunctional work, right? And as we are talking, definitely we are going to talk about the antenna part also. So definitely you can understand, because antenna is the last element. We will discuss in the few slides, just after few slides. So definitely your, not only antenna, your every wireless communication component, right? Every component need to be that much of advanced, so that it can support multifunctionality, right? So this is the some noise is coming, sorry. uh, okay, so this kind of functional multifunctional ability should have, right? Every component should have. It is not about the antenna, it is about the every component in the wireless change, starting from antenna, filter, mixer, and low noise amplifier, everything. So this is the most challenging part, and day by day it is getting more challenging, right? But definitely as a like as a electronics engineer, we as a or any like it is not a single engineer job, right? You can understand it's a multidisciplinary thing. So you have to have like communication engineer, RF engineer, PCB engineer, then the software part in when come, then computer science engineer. So and then obviously when you are talking about product, actually I'll going to discuss this part in the end more I will give more focus on that, that when you are going for a product, then what are the challenges you have to face. So as an engineer, you have to think lot of things, like maybe you are an RF engineer, but you cannot focus only on the RF performance, you have to focus on every other part, like starting from mechanical to other things also, production level also. I'll discuss those things. So this is the major difference when you are going for a product level engineering. Anyway, so then start with the 5G technologies. Basically already we are using, right? And right now I think almost everyone is using either Geo or Airtel or Vodafone, whatever. So what we are expecting in the 5G, as I mentioned, like first is data rate. So increased data rate is the first uh, like uh, thing that we are expecting. So it is the specification wise, when you are talking about 5G specification, increased data rate should be the first priority, right? So we are talking about right now 20 Gbps, 30 Gbps, like that. Okay, so which is 20 times faster than 4G. Maybe these are some theoretical values, maybe we will not getting exactly this amount, but you can expect at least that. Then obviously low latency, right? So the delay when you are sending some signal and when the receiver is receiving that signal, that delay, that should be very minimum. So this is the latency, right? That should be very less. Then massive network capacity, definitely we are now targeting because this is the problem or major issue for starting from 1G to 5G or 6G, whatever you say. The problem is the number of users are getting increased every year exponentially, right? So when there is a 1G or 2G communication, how many user per suppose you are per area you are talking about, so 1 kilometer area, suppose you are talking in that area, how many user are using mobile phone during 1G or 2G time, that number, and how many mobile phone are using nowadays, you can understand that there is a huge change, right? And obviously to accommodate all the user at the same time, because that how many user are talking at the same time, because I think nowadays every user is using at least one of at least near network. Okay, always our mobile network is on, every time it is on. It is during the 2G or 3G days, I know, like we have to very careful about the internet usage, right? Because these are very costly at that time, there is no unlimited thing. So when we need that, only that time we generally switched on our network. But nowadays it is not the case, you have to be on 24 into 7. So you can understand the number of user has increased. Also every user is using every mobile device at the same time. So definitely this capacity improvement is very important, and you can understand how much complex it is. So that's why massive network capacity right now, 5G or 6G is actually it will deal with that thing, right? So improved user experience, obviously we are now, we are very much familiar with this video conferencing, okay, and work from home concept, right? So user experience is very important. If you have low latency, if you have higher data rates, then only you can utilize that thing, otherwise there is no usage, right? Then enhanced security, obviously this is one thing. Encryption technique, new encryption techniques are coming, because when there is advancement in technology, definitely the the bad effect is also can come, right? So people can intercept some maybe some defense information, right? We need more encryption about that. We have to secure our data, because day by day we know that these are the scam are increasing, right? So the fraud are increasing. So we have to like we have to encrypt our data, otherwise it will be in some other hand. So then obviously the connectivity. So these are the major key features in like 5G technologies, right? Now whenever you are talking about any technologies, in terms of if you are talking about in terms of wireless engineer, then the first thing that comes into mind, okay, what is the band for that? So what is the 5G band right now? So the mostly using, you if you are searching in the in the open literature, you can see the most people are working in the 3.5 gigahertz band. That is the low band. Okay, low band. Then there is a mid band, and then is a high band. So worldwide wireless operators use low, mid, and this high three frequency spectrums are there. So bands with the lower frequency support longer distance and are less likely to blocked by the substantial object. But this is achieved by the trading of speed and capacity. There is a trend of always you cannot achieve everything with some technology, right? So you have to adjust or like compromise somewhere. So there is a like this trade-off between the speed and capacity. Okay, then mid spectrum, like generally over 3.5 gigahertz. So this band, when you are talking about this low band, then it can, as just I mentioned, you can use this band as for the long distance communication, because the as this is a very general concept that as we go higher in the frequency band, the losses will be more, right? So when you use high band, then you cannot achieve longer distance because of these losses. But what is the advantage is huge bandwidth. You can get huge bandwidth when you talking about the high band, but at the same time when you come down to the low band, you will not get that much huge bandwidth, but your operating area will be more. So that's why there is a trade-off. So depends on your technology, your requirement, which area you are working, then obviously you need to select. But right now we are talking about 6G communication or beyond communication. Actual 6G communication will maybe it will be at higher frequency, right? So millimeter wave range. So when we are talking about millimeter wave, definitely the first thing that comes in your mind, that is the uh, the losses. So you have to avoid the losses. Then your network capacity, actually, that the network, sorry, your range has decreased when you are talking about higher frequency millimeter wave. So as it is decreased, you have to install more tower to cover the area, more area. Okay, so that is the disadvantage, but definitely you will get more advantage because we are talking about more high millimeter wave. That means you will get more bandwidth, and that is absolutely necessary when you are coming to 6G and all. Okay, and MIMO is just a technique by which you can achieve multiple things. That's a separate thing. Okay, but we are talking about only the band, how to choose the band. Okay, then as I just mentioned, that signal attenuation is the result of like meteorological conditions such as rain, fog, turbulence. At the higher frequencies it affect. Why? Because as we move to the higher frequency means your wavelength is getting shorter, right? So millimeter wave, that's why it is millimeter wave, because the wavelength is in millimeter, and that's why it is very much affected by the raindrops and other things. Because if you just think about a raindrop, that radius will be in the millimeter range, right? And then that we know that when this two will be matched, when that wavelength is in millimeter, your that raindrop is in millimeter, definitely that will interfere, and that because of that you will get attenuation. So that's why signal attenuation will be more at higher frequencies. So as just I was discussing that when we are talking about this higher frequency band, then this you have to face this challenge. So I know like most of the people who in the BTech days, I think we all read this wireless communication subject, right? And in the wireless communication subject, the first thing that we read is the cell, right? Micro cell. Why this cell concept is coming when we are talking about, actually this cell concept has developed from 2G, part 2G to 3G. In 1G there is a omnidirectional antenna. So in the omnidirectional antenna, there is no concept of such cell, okay, because it is radiating same power in all direction. But after that, number of user are increases. So to accommodate the users, to increase the channel capacity, the people are now think about the sectorization. So it is dividing in a so one antenna is situated in a particular cell, and it is dividing into multiple cells. So that is why sectorization is there. So
Dr. Bhattacharya, you are not audible. I think you are muted from your side.
okay. Oh, sorry.
Okay. Ah,
Now it's okay, right?
okay now. Now. Okay.
Okay. Sorry. So okay. So as we are discussing about the cell size has increased cell size can be possible in the lower frequency, but when you are talking about millimeter wave, your cell size has to decrease, because you can, as I mentioned, you cannot go up after certain range because the attenuation is high when you are talking about high frequency. So the higher band allow is the increased data transfer rate, low latency, and increased capacity. This is the advantage of higher frequency. But the challenge in the millimeter wave is that higher frequency have shorter wavelength, which means that the signal are more prone to the fading by the object. So that's why like buildings or any kind of object. So these higher frequency signals are more prone to the fading. This is the more challenging part, and that's why you have to install more number of towers in a same area. That's why you see in the right side cell size are getting smaller when you are talking about the millimeter wave. So millimeter wave means we are talking about from starting from 24 gigahertz to 52 gigahertz, in that range, or the higher also. So it can go up to 100 gigahertz also. So we don't know like in the 6G which kind of band we are going to use. It is still in R&D stage. We all know that many companies, like many, we are working now. We are also is a 6G Bharat mission, right? From the government side also, they are providing more funds. Different institute are working, like IIT Madras, Samir, many institution and government organization. They are trying to now work on in this millimeter wave technologies, and we have a vision of like 2030, like by 2030 maybe we can see our own setup, say, millimeter wave setup in India. So we are hoping that we'll see that soon, right? Okay, so another issue in millimeter wave signal are most susceptibility to the interference wireless signal as meteorological condition that we already discussed. Why? Because of the wavelength is in the order of millimeter wave. So that's the problem. Okay. Then we can talk about some MIMO technology, but this is a very basic. I think everybody has an idea about this. Just to give a brief introduction, why MIMO, why we are using MIMO, because MIMO technology has emerged as a highly promising solution for the wireless communication, offering an opportunity to overcome the limitation of traffic capacity, higher speed broadband wireless network access, right? So to accommodate all these things like high capacity, the user number of user are increasing, and also high data rates. MIMO is a one technology, is it's a kind of wireless technology that can offer those advantage, right? So that's why if we apply the MIMO in our communication, this mobile communication part, maybe we'll get all this tip. Still people are using still people are doing research here, because uh, definitely when you are MIMO means multiple input multiple output. So when you are actually implementing multiple antennas, as you can see in this right side picture, you can see one antenna is there, MIMO antenna, like lots of antenna element are connected. I'm only talking about the antenna here. So you can see how many elements are there, and you can see also that blue lines where is connecting, that these are just connecting wires, right? So each cable is connected to the each element. So you can understand that this much of cable introduce high losses. So this is the major problem when you are introducing this more number of elements. Definitely the losses will be more, and this will definitely degrade your performance, right? Overall performance, because we don't want loss. But definitely when you are adding more element means more cable loss. So you have to compromise somewhere. So still that's why maybe the people are not getting that much efficiency which they are expecting, and that's why it's still in R&D stage. But definitely it will, near future we'll can see this kind of MIMO antennas in our mobile phone towers. Okay, so by utilizing multiple antennas at both transmitting and receiving end, MIMO system enhance the performance of the wireless communication system. It is established wireless communication technique for sending and receiving multiple data signal simultaneously over the same radio channel. So there are two basic concepts. I'll quickly discuss those things. I'm sure that people who are working in this MIMO, they can understand more easily that why MIMO offers more advantage. Uh, but okay, so in general we will talk about that, because in our today's lecture we will not going to discuss the MIMO antenna, but I'll show you some pictures that people are already starting research on this, right? Like big companies like Samsung, Huawei, those are already there in a race, we can say, that who can first develop this MIMO technology and get the higher data rates, right? So okay, so as I just mentioned, like there are two concept, like from theoretical point of view, why MIMO? Because MIMO can give you more efficiency. How is that possible? Very in a very simple term we can say, or in a way, if we want to understand in a very simple way, I think this is a very great diagram for that. So there are two, actually not two, basically three things, three major terms is here: spatial diversity, spatial multiplexing, and beamforming, right? So beamforming is a technique like which is basically when you are talking about this spatial diversity and spatial multiplexing, beamforming is the technique by which you can actually get this thing. So okay, so what is the difference between their spatial diversity and spatial multiplexing? In a very simple term, like spatial diversity means you are sending your same signal over over different antennas. Like suppose you are just for example, you can see some Wi-Fi signal are there, right? So you can see this Wi-Fi router. I think everybody is having this Wi-Fi router in other office or in home, and we can see multiple antennas are connected nowadays in the Wi-Fi router. Why? Because it will actually basically developing that MIMO communication between your receiving device and the transmitter. So why the multiple antennas? Why not single antennas? Here is the concept. Like in the spatial diversity, suppose you have two TX antenna, as you can see here, one red and another blue, and the RX side also another red and blue RX antenna is there. So same signal is transmitting over the both the TX, and that signal is coming to the RX side. But this same signal actually going through the multiple reflection from the wall, you can see. So some part of the signal may affect it when through the red tx, and through the blue tx some of the signal are reflected and it is coming to the rx side. But as same signal is transmitting, so if something is missing in the TX, that signal can be recovered from the, so suppose red TX, same signal can be recovered from the blue TX. So that is the concept. So after fading also, maybe you some part of the part is missing from the red TX and some part of the missing in blue TX. But ultimately, when you are combining that signal in the receiver side, maybe you can get all the signals. So whatever the missing in the red, that you can recover from the blue, whatever is the fading in the occurred in the blue, that can be recovered from the red one. So this is the concept of spatial diversity in simple terms. And spatial multiplexing means same signal, now it is divided into two parts. Suppose because two tx is there, two tx two transmitter are there, so the now the same signal is not transmitting. The same signal is actually, the signal is dividing into two parts, two separate parts. One part is transmitting so tx red tx, another part is transmitting through blue tx, and that finally receiving in the receiver side, and they combine. So the fading, when you are transmitting a small packet, suppose as a packet, if you think about as a data, it's a like so small part you are transmitting through tx1 and another part is from tx2, the chances of getting faded, that is very less, right? So this is two different techniques. Now uh, depend on the channel, what kind of channel through, what kind of channel through that signal is going, depend on that you have to decide which technique you are using. Now how you can actually when you are talking about the implementation, how you implement that spatial diversity or spatial multiplexing, through beamforming. So beamforming is that technique through which you can do, because we know beamforming is nothing but a lots of antennas are connected in an array, and you are particularly directed your beam in a particular direction. So we'll discuss a little bit about the beamforming also. So this is a very general concept, right, of the MIMO part. Okay, now let's talk about the antenna part. So we all know that antenna is the edge element, right? So in any kind of wireless communication, so it is like a transducer. You are giving some electrical signal and it is transmitting into the electromagnetic wave, and then in the receiver side just the reversing. The electromagnetic wave it is receiving, and it is actually transforming that wave into electrical signal, and in that way we can say there is a like the 1831, this year is a like magical year, because this is the, you see, electromagnetic induction was discovered by the Michael Faraday, and this is the basics of electromagnetism. We know that electromagnetic induction. And interestingly, you see, this is the year of birth for the father of electromagnetism, who is none other than James Clerk Maxwell, right? We all know that thing. So I think this, we should know as a communication or RF engineer, we should know at least these three people who actually change our world, right? The Maxwell, who developed this Maxwell's equation and this whole wireless communication theory, and then the Michael Faraday, who did actually, Michael Faraday obviously did this experiment before Maxwell, the induction. And then the Hertz is the first person who actually developed the practical antenna by understanding this Maxwell's equation. Okay, so this is the first picture. As you can see, the Hertz experiment, what antenna he has developed, and from there you know what changes have been done in the wireless communication. So these are three people who are the pioneer and in this wireless communication. Okay, so then coming back to our main topic, the base station antennas, right? So base station antenna is the edge element in the ER interface towards mobile terminal. All we generally everywhere we go we can see this kind of antenna in the tower, mobile phone tower, right? This big white color boxes we generally see in the tower. The size may be different because that depends on which kind of antenna it is it for working what kind of frequency band it is using, whether it's for mobile communication or for internet access. So depend on that different array size, how much gain you require, so that depends on multiple factors, in which area you are there, and lots of things are there. Anyway, our main target is the development or research in this antenna, and depend on the requirement we need to develop that, right? So there are, at the beginning I mentioned, like there are two major difference in the antenna when you are talking about base station: omnidirectional and directional. But nowadays omnidirectional antenna are not using, this is like 1G communication uses that thing. So this were, because why? Because at that time number of user are less, right? So we don't need high capacity, so that's why omnidirectional are preferred for low capacity and extended coverage scenarios such as rural areas. In contrast, the directional antennas are used to serve a targeted area, right? But nowadays everywhere it's a targeted, because number of users are increased, everywhere the user are there. So you have to make a sector on which you are actually targeting your beam. Okay, so to provide more efficiency or higher capacity. Sorry. So operating frequency band, generally which we use in the this mobile communication is coming, it's from 650 to 960 megahertz, and another band is 1695 to 2670. So these are generally in antenna it says like low band, mid band, like that we generally call like that. So low band means around 650 to 960, in that range. Mid band means this, or high, sometimes we say high band also. Okay, that depends on different allocation. So uh, with every generation we have introduced like new bands, okay, for the mobile communication. This is one thing. As we are discussing at the beginning, sectorization. Why sectorization is required? Because this is a great technique to improve the capacity. So this is a capacity improvement technique. Sectorization is one technique. So we know that this kind of hexagonal shape of sector we generally use, still now it is using, right? So in 1G this was omnidirectional, so there is no hexagonal like shape, or if it is a hexagonal, maybe one antenna is sufficient, because that's omnidirectional, right? So in the middle of a hexagon, if you place one omnidirectional antenna, it will radiate power in all direction. As the number of user increased in the second generation, from second generation onwards, the operator started consider the way of increase the capacity is the sectorization. To increase the capacity in 3G, this is further subdivided. Okay, so narrow sector. So you can see, if you divide a hexagon in 3 sectors, so each sector will be like 120 degree, right? 120, 120, 120, like that. But in 3G, as number of user has increased, so you need more capacity and more bandwidth also required. So they further narrow down this sector, and then this sector may be from 120 to 60 degree or 65 degree, like that. Or now even more you can do, like 60 to 30 degree or 35 degree, like that. So narrower the sector means you are increasing the channel capacity. Okay, so but the problem, what is the problem here? The major problem is overloading the tower, because you understand that you are sectoring means you are like adding more number of antennas, right? So when 3 sectors are there, that means 3 different antennas you are placing in one tower. When 6 sector are there, that means you need 6 antenna in one tower. So that is called the loading on the tower. So you are increasing the loading on the tower, increasing the cost, everything, right? So that also you have to think. So you have to optimize in that way. So depend on the number of user in that particular area, you can plan accordingly. So that is the very big part of the like this kind of thing, the planning that of the sectorization. Okay, how many antennas will be there, like that. Okay, then another capacity improvement technique, that is a very effective technique, and till now we are using the same thing, same technique in 5G also. That this is called polarization diversity. And I know the people who are working in this antenna RF domain, they very much know about this polarization of the antenna. So it is okay, I let me check I have the slide for that or not. Okay, sorry. Okay, so anyway, that is not a like big thing. Polarization means in which like how your electric field is actually changing, so in which plane your electric field is oriented. Okay, that means if your antenna is vertically placed, and suppose your polarization is vertical polarization, then if your antenna in the transmitter end, if your antenna in the receiver end in horizontally placed, that means horizontal polarization is there, then your antenna will receive zero power ideally. Okay, so this is very simple thing. In that way you can think. So your antenna has to properly aligned with respect to the electric field, how the electric field is transmitting from the antenna. So or maybe electromagnetic wave, the orientation of VM wave, you can say like that. So if it is vertical polarized, then your receiver end also has to be vertical polarized. If your transmitter end is horizontal polarization is there, then also it should be horizontal polarization in the receiver end, so that you get the maximum, you receive the maximum power. Okay, so the aim was to provide two orthogonal polarization in the antenna array. The horizontal, so you can understand when you are suppose at the same time or from the same area, if you are transmitting both horizontal and vertical polarization, so your receiver antenna will not interfere, right? So because depend on the orientation, it will receive the power. So a vertical receiver will not accept the horizontal polarization signal, because it will be very less, the amount will be very less, so ideally zero. So the horizontal and vertical polarization were initially used and in the 2G, but then people have switched from vertical and horizontal to 45 plus minus 45 polarization, and still now we are using plus minus 45. So when you are designing the different antennas for any communication, we generally consider plus minus 45 polarization for the any kind of base station. Okay, so otherwise it's, so it is known as a slant polarization, right? So and it has been widely adopted in base station since 2G, as I mentioned. In the right hand side, you can see this actual antenna. This is an actual antenna element. It is purely made of like aluminum or conducting material. Okay, so it's a, you can see it's a full metal antenna. You can see the picture. This antenna is a full metal antenna. There is a reflector plate that is also metal, so there is no dielectric or other material involved. It's a full metal. So that's why we prefer full metal, but it is not all for all case. I'll show you some different antenna also. This is basically used for the high frequency, and full metal advantage is that you will have low loss because it's a full metal, right? There is no loss for the dielectric. So that's why this kind of antenna used for like high band uh, antenna design, and this is a very common shape actually, plus minus 40. You can see it is noted here, like how plus and minus 45 is oriented. Basically it's a dipole. Generally it is called dual polarized dipole antennas, and in general dual polarized dipole are used in antennas, in base station antennas. So why it is dual polarized? Because at the same time this antenna can transmitting or receiving plus 45 polarization and minus 45 polarization. So you can see how the dipoles are oriented, right? So and in the left hand side picture, you can see what is the difference between a vertical polarized array and slant polarized array. Okay, so today the polarization technique is like a very favorable choice, and in operation one polarization used for transmission and another polarization used for reception. As I mentioned, there will be no problem because polarization are different, so it will only interact with the respective polarization antennas. Okay, so this is a very great, because in a previous days two separate antenna you need to use for transmitting and receiving, but you can see here only single antenna, but it is a dual polarized. That's why at the same time it can transmit and receive. Okay, so in doing so, one dual polarized antenna is more, it is sufficient to achieve diversity performance instead of using three linearly polarized arrays. Okay, three different arrays. So this is one great technique to improve the capacity. What is the basics of array? Because why we need the array basics? Because we know that array, this kind of base station antenna, only single radiator is not sufficient. We need to use array. Why? Because we need to focus our beam in a particular direction, and that means we need more directivity. Okay, so to directive our antenna beam in a particular direction or to achieve more directivity, array is a very basic concept in the antenna, right? Array means nothing but a similar kind of element you are connecting. Okay, in a particular manner, with a particular distance and amplitude, phase, all these things you can control, and by controlling those things you can change your beam from one direction to another direction also. When you are changing your beam, that is called phased array antenna. Why it is called phased array? Because by changing the phase of the individual element, you can shape your beam and you can direct your beam in a particular direction. So we know that there is an array factor, right? It depends on number of radiating element. the element spacing, and amplitude and phase distribution of the each individual element. In the figure, you can see in the top figure, you can see, when you are using a single array, it is that the radiating power is equal in all direction. When you are using three antenna in an array and you are combining all this thing, you can see you are directing a particular beam in a particular direction, and in other direction the radiated power is less. And in the another picture, you can see there are 5 antennas are connected in one array, and or 6 antennas are there, and you can see you are now getting more directivity. So this is very general concept, that when you are increasing the number of antenna elements, you are getting more directivity in a particular direction, but obviously your bandwidth is, your beam width is getting narrower. So definitely it depends on which kind of application you are using. Depend on that, you have to choose which kind of bandwidth you require, or beam width you require, how much gain you require, how much directivity you require, and accordingly you need to choose how many antenna element is you need to design. And how you move your antenna beam, you see, antenna beam can be moved with the help of phase shifters. So when you are connecting phase shifter to the antenna, you can shift your beam. And what is a phase shifter, what is it doing? Basically it is changing the phase distribution of individual element. So by changing the amplitude distribution, you can change the directivity and side lobe levels, everything you can control. And by changing the phase distribution, you can actually shift your beam from one direction to another direction. So when you are designing a base station antenna, you have to design everything. You have to design phase shifter, you have to design your antenna element, and the cable planning, amplitude distribution, everything you need to consider, and then finally you will get. That's why base station antennas are so complicated to design, because it's a phased array antennas. uh, as I just previously mentioned, that when you are talking about antenna loading factor, right? Then one thing you can do in a single antenna, you can apply multiple antenna elements. You can attach multiple antenna elements. Now this is very common technique nowadays, where in a single antenna, that's why you see sometimes antenna size is bigger, sometimes smaller. Why? Because in that single antenna, it is not about the single frequency. It may have some low band, some high band element, low band element, and sometime it may have three different antenna elements also. So one high band, one mid band, one low band, like that. So operating frequencies are different. And you see very interestingly from this figure, in the below figure, you see the cross shape. One is called low band array, and another green one is the high band array. Why high band is smaller in picture? It, definitely there is a reason. What is the reason? Because high band array means the frequency is high, that means the wavelength is smaller, and we know that antenna size is generally controlled by the frequency. So if high frequency means low small wavelength, the antenna size will smaller. That's why you see high band arrays are smaller, and the low band array, it means low band means low frequency, so large band, large wavelength. As the large wavelength means antenna size will be larger, and that's why you see low band arrays are here. You can, from the picture you can see it's showing larger. So this is called multi-band array, and this is like separated, but they all are installed in a single reflector. Okay, I'll show you the picture in the next slide, few slides. I'll show you some picture where you can see this low band and high band array in a single antenna. And obviously you are the first question that comes into your mind, that okay, we are attaching all the antenna in a single reflector or single ground plane, that's fine, but definitely it will interfere. Yes, it will interfere, and that is the major challenges in this base station antenna design, to minimize this interference. And still I can say you, the people who want to continue the research here in this base station, they can still have a chance to do the research in this particular thing, how to mitigate this isolation between two different arrays, or sometime two. See the high band array 1 and high band array 2 is there, right? In the right side picture you can see. So there will be interference obviously, but it is the most challenging part, how to like minimize that interference. So people are now using different resonance structure, metamaterial based thing. These are the some techniques, are some separation wall you can place, but it is not a fixed. Okay, there is no fixed way. You have to do some research and you have to understand why, what kind of structure is best suiting. suited for this, because you know that one resonance structure you can apply, but it may interfere the high band also, so you or a low band also, so you have to think a lot of things comes into picture. You have to think everything, you have to consider everything. Okay, so this kind of technique, still we are using different high band low band array in a single antenna to accommodate more antenna in a space, so that your antenna load in the tower will be less. From obviously the cost is also a big factor here, right? In a single antenna, if you are placing all the antenna elements, that will maybe save your cost, right? Okay, now these are some if fabricated model, a simulated model that is for the base station antennas. Generally you can see in the open literature, uh, people are doing more, lot of people are doing this kind of antennas. In the top side you can see these are the FR4 based structure. So basically they are fabricated with the help of dielectric. Okay, so with the help of microstrip technology, this kind of dipole structure are, these are and let me tell you, these are all dual polarized dipole. Okay, so all are dual polarized dipole antenna fabricated in some substrate, dielectric substrate. And also I have shown you in the previous slide, shown you that full metal structure. So depend on application, depend on the requirement, you can develop, because as I mentioned, this FR4 based substrate based structure is easy to design, easy to fabricate, but it introduce some losses because dielectric is there, right? You can see this is the real picture of some antennas. When you open that base station antenna, you can see this kind of array antenna, right? And you see how much closely spaced they are, right? So this is very important to get more isolation between one column to another column. Maybe in the picture you cannot see the decoupling element. There is some kind of decoupling element are placed in columns. I will show you in the next slide. I have some pictures for that. Yeah, you can see these are the components that actually I have taken all this picture in from my lab. These are the some antennas developed by some, like some China's company or some other company or US companies. So we have opened the antenna and we have seen that what kind of technologies they are using. You see, these are the component of base station antenna. So it is not about only the radiator. When you are talking about base station, there are a lot of different components. So starting from phase shifter, decoupling structure, power dividers, different radiators, decoupling element, lot of thing you have to consider. So this is a full array. You can see in the right hand side, full array. You can see there are 4 different columns are there, and in between column you can see there is one separation wall kind of thing. And these, as I mentioned, these are walls are needed to get the more isolation between 2 columns. These are some measurements facilities that I was talking in the beginning. Actually Ericsson has set up these facilities. Some of the from Ericsson side, some of the ACL own fabrication measurement facility we have. So yeah, these are some really interesting, and you need to place all the antenna here inside the anechoic chamber, and these are all automatic process. You just need to click one software based interface is there, and you just need to click and automatically you will get all the radiation pattern, everything. But you see this antenna, when you are actually, this is the front side. When you look at the back side, you can see the linear phase shifter, all this connected in the back side. So you can see all the cables, power divider, everything is connected at the back side of the antenna. Now as I was mentioning, the reflector plate, right? Why this reflector plate is important? Because otherwise your beam will be interfere in the backside, right? So we don't want any back lobe. We want to direct our beam in the front side only. So that's why this kind of large reflector plate is required, and you can place your the phase shifter, cable, power divider, everything at the back side of the antenna. Then the interference will be less, almost zero, because your metal plate you are using. So your every back lobe will be reflected back in the front side. So this is a thing. Okay, here as I was discussing, the all the components I have noted here: reflector plate, phase shifter, and there is some very interesting thing that is called rate. Some electromechanical system was there. Generally we use this kind of structure, electromechanical structure. Actually why it is used, it is connected to the phase shifter, because these phase shifter, as you can see in the right side, these phase shifter are electromechanical phase shifter. That means it has some particular electromechanical system through which we change the phase of the individual element. Okay, so because this phase, from this phase shifter, this cable are connected to the individual antenna array element. Okay, and how you will change the phase? So electrical, actually you are giving some electrical signal to a motor. That motor will rotate, and according to that rotation, your phase shifter, actually in this kind of phase shifter, one dielectric plate is there. Okay, inside that dielectric, when you are changing the position of the dielectric plate inside the phase shifter through that motor, actually the phase will change, and through that you can actually change your beam from one direction to another direction. So in this kind of antenna, generally we switch our beam from, say, suppose minus 10 degree to plus 10 degree, or minus 5 degree to plus 5 degree. In that way we change our the beam, the beam direction. So to change the beam direction, we generally give the electrical signal to the motor, and that motor will control this phase shifter. That's why I'm calling it as a electromechanical phase shifter. Okay, technique generally used, but all these things are installed or connected in the antenna itself. Okay, we are just giving some electrical signal and everything is happening inside that. That's why the back side of this kind of antenna are so much complex compared to the front side, because in the front side only you can see the only antenna elements you can see, but when you rotate the antenna, you can see that this cable, phase shifter, electromechanical system, lots of power dividers, everything is there. So the backside is more complex. But together you have, when you are talking about base station, you have to talk about, as I mentioned, everything. So together it's a system, right? So then what are the challenges? Obviously the challenge means you have to achieve every parameter in a very specific way, because when suppose a customer come to you, suppose Ericsson is coming to us and telling, okay, you have to design one antenna which can achieve this characteristics. What are the characteristics? Starting from impedance, bandwidth, isolation, gain, beam squid, half power beam width, beam steering, cross pole, front to back. There are, I'm telling you, at least 15 to 20 parameters. So, and this is the biggest, as I mentioned in the beginning, I'll discuss that thing. So that what is the difference between academic and industry research? Here you can understand, when you are talking about the academic research paper, we do not consider that much of parameters. We generally focus on more gain or maybe beam width, and maybe the port parameters like isolation and matching. That's it. These 3 and 4 parameters are okay with us, and we can easily publish a paper. But the problem is when you are talking about the actual implementation of the antenna for particular application like base station, you have to meet at least 15 to 20 parameters, different antenna parameters. Every parameter has to meet, and then only you can implement that thing and you can use for a practical application. And this is the major challenge. As I mentioned here, the few of the major parameters, right? For the base station, front to back ratio, cross pull, beam steering, beam squint is there, then upper beam with 3 dB beam with 10 dB beam with bowl vertical plane, horizontal plane, lots of things are there. Okay, so all the parameter you have to satisfy from your antenna, and then only your antenna will be approved. Okay, so this is the major challenge, because you see, you can understand, this is not a easy task to get all the parameter in a particular range, but we have to adjust, we have to do something. So that is the challenge in every project, that is the challenge. Okay, so okay, that as I was mentioning that very few companies or big companies are there who are already started developing this 5G MIMO antennas, right, for the 6G and the next generation communication. You can see some of the uh, pictures I have just taken from the internet to show you that, okay, so like Samsung, Huawei, they are already started working on this, and the prototype they have already built, and maybe it will be in market in next few years. Okay, these are the these are base station antennas, big antennas. Now talking about some small antennas like 5G antennas for MIMO, because you are implementing MIMO antenna in tower, but definitely you have to receive the signal in your phone also. So definitely then you have to design your antenna for mobile phone also, right? So different antennas, different type of antennas that you can see here. So Qualcomm has developed for some mobile phone. Then people are working with the DRA, people are working with the SIW based antennas, but these all antennas are for mobile phone applications, okay, or smaller electronic applications. So yeah, so just to show you that people are working here, and there is a huge scope of doing some research in this area, because still it is in R&D state, right? So these are the like radiation patterns when you plot. I think antenna people are very much familiar with this kind of plot. So just to show you some of the important parameters, like what is beam squint, what is cross pole ratio, what is front to back. These are the things, 3 dB beam width, 10 dB beam width in a single graph. I think it's a very good representation how all these things you can calculate. And you, as I mentioned, you have to meet all the specification, then only you can go for implementation, okay? So this is one thing. So the challenges are there, definitely challenges are there, but obviously the solution are also there, and that's why we can doing this research for last I think small some decades. People are doing research, so definitely they have solution. But I can tell you, still we are facing problems, still some solution do not work sometime. So you have to think about some different solution, and that's why we need some more research on this base station antennas also. So here you can see some of the design challenges and some of the solution, but this is not all, right? You have to think about it, other things also, but these are some different general solution technique for these design challenges. So the challenges comes first with the impedance bandwidth, right? You need wide bandwidth, you need high isolation, you need more stable power beam width over all the frequency range, then front to back ratio high, minimize the beam squint. But you see, achieving one goal is even difficult, and achieving all the goals is, obviously you can understand how much difficult it is. So every day I see this kind of challenges people are facing in our company, and they are trying to manage somewhere, but we have to compromise somewhere. Maybe we are not achieving that much of half power beam width, but we can getting more isolation. So that depends on different application, you can compromise. So maybe the Ericsson is saying, okay, you are achieving that half power, we are okay with that, but we need 1 dB more isolation. Then you have to work on that. But doing so, maybe you are seeing that other some parameters are getting affected, maybe your matching is getting affected, so again you have to redo that thing. So this is the challenge, you are trying to perfect one parameter, other parameter getting affected. So the first thing is, obviously when as a antenna designer, first thing when the challenges or the requirement comes, they are saying, okay, we need that much of gain, maybe 18 dB gain we require. So to achieve 18 dB, how many elements we can design for that? So maybe we have decided that, okay, 10 element is sufficient to achieve 18 dB gain. Then 10 element means single element, how much gain you are getting from single element, that you need to calculate. Then how much isolation you are getting, and from that single element, what is the power beam width of that antenna. In that way you have to start, okay, and then slowly you have to design your array. Then one array is coming, then another array you place, and then you give some isolation technique between to get more to minimize the cross coupling between two array. In that way it works actually. In that way you have to start slowly everything, okay. So what are the future trends in this? As already we have so much thing we have discussed, that MIMO 5G and MIMO 6G, these are the latest thing that comes into picture. So there is a huge scope here in the when you are talking about MIMO antennas, like doing some research in the MIMO technologies, smaller millimeter wave antennas, because still we can see whatever antennas are using in 5G communication, still we are in low band side, okay, up to 2 gigahertz or 3 gigahertz. But when you are talking about millimeter wave, as we know that millimeter wave means your every single component will be smaller, right? Starting from antenna to every other electronic components, and that is the big challenge. Not only the design challenge, there is fabrication challenge, everything you have to accommodate in a smaller area. So when you are talking about millimeter wave antenna, that is the challenge, because the everything is getting smaller. So so design is not easy. And when you are talking about MIMO, as I mentioned, like MIMO means a lot of elements, so you have to accommodate, means losses will be more. So you have to think about that thing, because MIMO is when you are multiple antennas are there, the major challenges is the power combiner or something like that, because you have to combine all the thing, all the element power in a single combiner. So designing a power divider, power combiner, those things will be a crucial part. Okay, so possibilities are open. Like nowadays people are like more doing more research on frequency selective base surface for the this beam forming and all. So this reflectory antennas, right? So these are the latest thing, antennas research that you can perform. And obviously active beamforming or reflectory array is, I think, the future of 6G antenna. So I think there are a lot of scope here. And also now people are talking about uh, like AI based designing, right? So I will come here actually later. So but before that, I think I should discuss this thing. What is this different between academic and industry research? Already I have discussed few things, but you can see the lower picture, in the lower side you can see that this below picture is some MIMO antennas, which the maybe some PhD research. Okay, this is an example of PhD research, and the top two figures are the real MIMO antennas or base station array uh, from Ericsson, which actually use for like any mobile communication. So just by looking at these two picture, I think it's easily understand that okay, the design process is not simple, right? When you are designing for any practical application. As I mentioned in the beginning, that the major difference is that now you do not only you have to think about your performance of the antenna or performance of your device, you have to think some other part also, because the first thing that comes into your mind, that is the mechanical part. Because now you have to work closely with the mechanical team. Suppose you are doing something, some design, and you are say okay, this design is gives very good performance, but your mechanical team will say no, we cannot fabricate that. Then you have to they will say okay, you cannot go beyond 2 millimeter. So you have to reduce to 2 millimeter. Maybe originally you have seen the 3 millimeter is giving more good performance, but mechanically saying no, 2 millimeter is the limit, so you have to again change. So here this is the problem, you have to think about the product. So productivity to like work for a product, uh, you have to think not only the performance, as I mentioned, you have to think that how much cost involved in there here. Okay, so as just I mentioned, like we can use metal based antenna, or sometimes we can use dielectric based radiator. But maybe your cost wise we can see that okay, dielectric based radiator is more efficient because the cost is less. Then though your metal antenna is giving good performance, but you have to switch to the dielectric part. So I am telling you my experience, because when I joined in ACL in 2022, my first project was filter design. Okay, filter design for a base station phase shifter. Okay, there is a R&D project for Ericsson phase. My seniors are already developed the phase shifter, but that some people actually tried to design the some filter, but they could not achieve that much of bandwidth, and they just skip that part. But when I joined, so my boss told me okay, you have to design the filter. It has a very high bandwidth, and people are trying, people at that time people were tried, but they could not achieve. So that come to me. I never designed filter in my PhD, so I know the basics, I know the theory part, but I never designed it. When I started design, it took me long time, because first I need to understand the software, because at that time I did not have that software access, so I did not know about how to design that in that particular software. Okay, first I learned the software, I started design. It took me at least 2 months to complete that particular filter design. And then when we showed to the Ericsson, what they told, that no, your trace width is only 1 point, it is based on strip line technology. I designed it, that line width was 0.8 millimeter, the minimum line width. And they told no, no, you cannot do with 0.8 millimeter, it has to be more than one. It will take 1 month to optimize that thing, because in RF domain, people who are working, they know in 0.1 millimeter change also, it can be a very like drastic effect in your antenna performance or any kind of performance. And filter is a very sensitive thing, because filter is nothing but a LC circuit, right? LC resonator. So LC circuit means you are changing some width, means you are changing the either L or C values. So definitely your performance will be getting affected. Again, it took 1 month to optimize up to 1 millimeter. We optimized that one in 1 millimeter. I get good performance. Again, when I showed that thing, they told no, we cannot accept this because we need 1.5 millimeter. Why? Why they are keep changing? Because this phase shifter is in the input section of the base station, and as you know, in the input section you are giving high power, right? Because it's a base station, it's not for a short communication. So high power you are giving to your antenna, so your antenna, that smaller width cannot handle that much of power. So to handle a high power, you have to have high or large width in the strip line. So I was so frustrated, I just reject all my design, and again I redesigned the whole filter. Again it took 1 or 2 months to complete, but finally I designed one filter having 1.5 millimeter smaller width, and it achieved a very good isolation. Whatever their need, it satisfied, and yeah, they are happy. My boss was so happy, because ultimately we have designed, but it took around 5 months. You can understand, a small filter took 5 months, because there are some very other challenges also. Because as I mentioned, there is no free hand, okay? Because everything has mentioned that you have to achieve this much of bandwidth, you have to achieve this much isolation, insertion loss, you cannot go beyond this thing, uh, you cannot edit any material, you cannot select your dielectric as per your choice. No, everything is specified by the Ericsson, suppose any customer, whatever the requirement. So as per their requirement, they have specified everything. So this is the major challenge, right? As an academic researcher, maybe you have a free hand, you can experiment with anything, right? Whatever thing is giving good result, you choose that. But in industrial research, this is the problem. Because as I mentioned here, mechanical themes comes into picture, then cost is a big thing. So accordingly you have to decide what technology already we have, you have to use that. Maybe you cannot do anything, because new thing, doing new thing is maybe very it will be very costly, right? So cost is the major part in in kind of product based research, right? So by thinking all this thing, you have to do your research with this limited or more constant is there, or limited amount of information, or suppose what I say, like a limited amount of mm, technology, we can say. Okay, so because we cannot do anything, so with the help of the specified range only, you have to perform, and also at the same time you need to get the performance. So this is the major challenge which I faced at that time. But finally when I achieved that, with all specification, whatever specified they have specified, with all specification and multiple constant, finally when you achieve that thing, it feels so good, right? So as a researcher, then you think, okay, I have done something which is really useful for some application. So this is the major difference. Yeah, that, and another thing that I want like to mention here, that is the timeline. So in academic, when we do PhD, we know that there is no timeline, right? You can do your research maybe up to 1 year, 2 year, 3 year, and then you publish your paper. Nobody is telling why you are taking so much of time, right? You are getting fellowship, it's okay, we are happy with that. But the problem in the industry is that, first thing, that the constant is the timeline. Okay, so here people are not talking about 1 year, 2 year, they are talking about 1 month, 2 month, like that. So they will specify that in 1 month you have to achieve this performance. In 1 month you cannot achieve, means they will simply take your project from you. So they will give the project to other company, so you will lose the business, right? So you have to do the business. That means you have to continue your research in such a way so that you can satisfy their requirement within the timeline. So 2 months means 2 months, maybe it can extend up to 3 months, but that's it. And you have to give some proper reason also, right? That why it is taking 3 months. So they definitely, they are also doing research. They know in this many months you can maybe do that thing, because they are investing on you, right? They are giving a daily basis amount. Okay, so they will not uh, definitely allow you to do research for an infinite time. So that is the major problem in industrial research. You have a very tight timeline, and in that timeline you have to finish your job. Okay, so this is the major difference. And yeah, you have to satisfy all the criteria also. This is a very big problem, but anyway, this is people are doing in that way, and people are doing business in that way. So this is a strategy, and this is the business thing. Okay, we'll don't want to discuss, but the main what I want to say is that they're the time constant. This is the first thing that comes into picture. Now they will not check that in which way you are doing, whether you are simulating or you are using some AI based tool. That doesn't matter. You have to get the output. That's it. And the last slide for me, like what are the problem statement? I have written some 3 problem statement for the students or researchers. Yeah, it is just a generalized problem statement, but you can definitely you can explore more. So if I talking about only that this dual polarized dipole, I can say still there is a need of more research on this high gain compact and wideband dual polarized antennas having good isolation, good matching. Still there is a requirement. People are doing for so many years, but still I would say there is a huge requirement for this. And now one thing is that only simulation is not sufficient. Because people are now using AI based script. Okay, that AI based script maybe do your simulation more simple. Okay, so maybe some steps you don't need to do, some optimization technique you can do that thing. Okay, the design optimization can be do with the help of some AI based script. So now people are now trying to work on that. So you have software, you are trying to implement some Python based script. Suppose you are giving to the script to the software, and software automatically optimize your design, so you don't need to invest time. So now there is a huge requirement to understand how we will integrate this AI based solution with the hardware part. Okay, recently in my team, one guy, he's from measurement team. He has done only btech, he's not done any mtech or phd degree, but he knows the programming part. So what he did in the as he actually, I really want to give this example, because recently he has developed some script he has developed that is very helpful in measurement. Why? In the measurement, our one very major requirement is side lobe levels. You have to achieve very low side lobe levels, and that is a very mechanical process. So you have to first measure the side lobe. It is not there, then you have to change the cable. Mechanically you have to change the cable, and you have to check, because by changing the cable you actually amplitude you are not changing. By changing the cable you are changing the phase distribution of the antenna, and by doing so you can achieve up to certain level of side lobe distribution. So we know, so that person has developed some Python based code which actually can do this mechanical stuff for it can calculate those things, and it can say you that okay, this is the cable length you can apply in the antenna, so that it will minimize. So that mechanical part will be very much like the time taken for the mechanical part is very much minimized. So right now he is saying that with the help of his script, now you can get the idea, okay, how much approximate my cable length will be, so that I get this much of side level. So he's telling that he has already tested, so we need to check that very recently he has developed. If it is working, that you can understand the time it is taking, maybe 1 day or 2 day to optimize the side level, now it come down to 1 or 2 hours. So you can understand how much efficient it will be. So right now there is a huge requirement for this, that so AI based script, if like computer science engineer and RF engineer need to integrate and do this all this measurement process. If you can automate some measurement process in that way, there is a like huge demand for that, and in future actually it is required. And also not only the measurement, in the simulation also, day by day you can see like generally we use ANSYS software, right? ANSYS is a very worldwide, it is used for wireless communication system design, RF design. So in the ANSYS, they are every year they are now trying to implement some optimization, some AI based thing. And in future definitely something will come where you even don't need to even design the antenna. Maybe some templates will be there, you need to click and it will all automatically do this thing. So it is red alarming for us all, because definitely as an engineer, then you have to understand the AI based thing also, right? Only focusing on the design it will not be helpful. So these are the future trends, and people who are really interested, they can implement, both interested in both programming and this measurement part or simulation part. If they can integrate both this thing, and I think they can do the magic. So this is a really important thing to know, and people are already started working on that. So that, as I mentioned, time is the major part in industrial research, right? So if you can minimize your simulation time, you can, if you can minimize your measurement time, that is what a big company want. Okay, the big like as I mentioned, Ericsson, why, Nokia, they all are working towards that. Not only research is one thing, but how you minimize your time to get the result, that is also important. So this is the future trend, I will say. Okay, so okay, these are some references, and yeah, and the person without whom I think the wireless communication, this topic is totally useless. I think this Jagadish Chandra Bose who developed this, because when you are talking about millimeter wave technology, I think he is the person who first demonstrated millimeter wave communication long back, when people don't have the idea of wireless communication. But we all know what is his story, I don't want to get again. But the thing which he demonstrated at that time, people don't know about the antennas and wireless thing also, but he demonstrated millimeter wave communication. And still it is very strange that how he has developed or how he has measured that high frequency at that millimeter wave frequency at that time. It is still as a mystery. But anyway, thank you so much. If you have any doubts, you can tell me right now.
Thank you, Dr. Bhattacharya, for your very much informative session and eye-opening session on MIMO antenna design. And there are few questions. This is for question and answer session.
Yep.
There are few questions asked. Mr. Sri Ramu TS is asking that what are the parameters that can be automated using Python programming? I do RF simulation and a Python programmer.
Sir, I work on MIMO antenna RF simulations, and I'm a Python programmer.
Yeah.
So I want to extend my research. So can you suggest what are the things that can be done new with programming?
Yeah, so as I mentioned, like I am not that much familiar with the program part, but yeah, definitely the right now, as I just give you some example, this is the measurement part, but maybe you are asking more about the simulation part, right? That what are the things you can implement in simulation with the help of Python script. I don't know which kind of software you are using, but anyway, nowadays in every software I have seen that they Python script, they are actually they can integrate. So maybe with the help of MATLAB also you can integrate some Python script to optimize the antenna parameters. Like definitely different antenna parameters are there, but suppose you are designing an array antenna, and suppose you want to get more you want to get less side load levels. So when you are asking about side load levels, definitely what features you have to target. The target is to get more amplitude distribution and suppose phase distribution. So all these things are connected to your antenna design itself, right? The radiator level itself. So manually we do the antenna designs thing. Manually we change any parameter, but without doing any manual, maybe you can generate some script which can automate this optimization process, and it can you can give some target. Okay, I need this side lobe levels, then how my antenna design will be, or how my amplitude distribution will be. So it can automate that process. So now that depends on which kind of antenna you are using, which kind of or RF circuit you are asking. Right now I know the in the
Sir,
ADS you can, yeah.
as of now, I'm using HFSS for my simulations, for my
Okay,
PhD simulation. So to reduce the side lobe levels, I'm using the defected ground structures.
yes.
Maybe I think that the same thing could be done with programming if I am
Right,
right.
right, right. I
That
can give
dimension.
you one thing. I can tell you one thing. Like actually, I have seen this kind of project already have been done in our ACL group. So I can tell you one a very good example of that. Actually, there is a requirement from the Ericsson that they in the as you are mentioned HFSS. That's why I'm telling, because we have done this thing for HFSS, both HFSS and CST. Actually, they told that like with the help of Python script, one team actually has developed some script which actually easy or make easy the design process. Like suppose you are using SIW based structure, so lots of bias are there, right? Suppose you are inserting some bias some particular position, or you want to delete that position, so lots of bias are there. Now they have some programming where you, if you just simply click, by one click you can eliminate lot of bias, or you can add lot of bias in a particular position. So they have developed some process. Suppose you want to give some port assignment, so they have developed some techniques so that this process will be more faster. So in that way you can think. I'm not sure that whether they are commercialized or not, but I have seen this kind of thing they have done with the help of Python script. And as you mentioned, defected ground structure, like defected ground plate can be any type of shape, right? It's not a fixed shape. That shape you can optimize with the help of some optimization technique, and that you can generate with the help of Python script maybe. So these are the things I can suggest right now. I don't have that much idea about that, but people are trying to like do this kind of thing right now. I can see.
Yeah. Well, the only reason I got interested is because I do programming with Python. And
Okay.
what are the libraries that I can use it for my RF in Python? Can I know if you are familiar with?
No, sorry that I'm not familiar with that. Maybe you need to search.
Yeah. I
Yeah.
need to explore more on that a little bit.
Yes.
Okay, thank
But these are the future trends. You know, that is a very good thing. You are exploring. Maybe some part you are the first person you will going to search, right? So
you.
yeah,
Exactly.
that will be very interesting. Yeah.
Thank you, sir. Thank you, sir.
Yeah.
Uh, Anybody else to ask Dr. Bhattacharya for any queries? Please go on. Do anybody have any questions regarding this topic to Dr. Bhattacharya? You are feel free to ask. I think nobody is there to ask any questions further. So I'd like to thank Dr. Bhattacharya for his very beautiful session and beautiful presentation.
Thank you. Thank you so
And
much.
we have a small greeting for you on behalf of your on behalf of our institute, Dr. Sudhir Chandrasuri Engineering College and Sports Complex.
Yeah.
This is for you, sir. Please accept it.
Yeah, definitely.
And
Thank you so much.
I will send you via your email later.
Okay, sure.
Okay.
Okay, thank you for
Yeah.
this nice session, interactive session. And I think people, if you have any doubts on anything, you can mail me. I think someone is asking. Okay, you can get my mail ID, no problem. Anytime we can connect, no problem, because we are all doing research in this domain. So definitely, we can talk, we can continue our research. So yeah, anytime we can connect, no issue.
Okay.
Yeah.
Thank you, sir. Thank you for your interactive session. And